Hello, everyone. Sorry, just didn't want any feedback. We are now live on YouTube. Welcome to your June edition 2020 of Insider's Guide to the Galaxy. You know the drill. Put your name, where you're from, and how your skies are. If you've done any viewing, have you seen any Messier objects in the chat? And we will get started. Hello, everyone. We'll let people file in. We'll give you a minute, but while we're waiting for everyone to file in, we're just going to our big announcement from National. As if you're on our email list, you already know we have the General Assembly coming up. So for those of you who don't know, the General Assembly is basically the annual meeting of RASC centers and just members and people who love astronomy and want to get together and chat and hang out. For the last two years now, this will be our third year that it will be virtual. This allows more people to attend. I'm just going to show you quickly where you can find out more information about the RASC General Assembly. So it's rascpa2022.ca. Tickets are on sale now. Sorry, there we go. Tickets are on sale now. It's June 24th to June 27th. We are jam-packed filled with events. We have events for members of the RASC. We have events for new astronomers in the general public and for youth. So to find out what we're up to, you can always go to events and click this schedule. We are doing 3 times more than we have in the previous years. And Chris will be presenting on the Saturday. We also have our Helen Sawyer Hogg lecture, which we are hosting this year with our speaker, Natalie Ouellette. And we have a keynote speaker for every single night of the GA, which is really exciting. Tickets you can find here. They are $20 for members, $25 for the general public, and $15 for youth under 21 years old. We also launched today the Astrophotography Contest, which is as long as you've taken the images and processed themselves and it fits under one of these categories, you can submit as many as you want for a chance to win a coupon up to $50 off any item in the RASC store. And all submissions will be featured on our GA website and in our GA social space. And for RASC members, our annual general meeting will be happening on the Sunday. So it's free to register. You don't have to be registered for the GA or pay for it. Come to the annual general meeting if you would like to say and voting on and hearing what is going on at the board level. So there is my little spiel, and I hope to see you all there. This is a big project all of us at National are working on and super excited. And with that, I'm going to pass it off to Chris so we can talk about all the globular clusters that for some reason I can't find in the sky.
Hopefully by the end of the session, you'll know how to find. I have at least one I can guarantee you'll find with no problem at all. That'll be part of our Globie Awards. So I thought we haven't covered globular clusters before, and they're one of those things that people may just take for granted because they most people might think they all look the same. When you've seen one, you've seen them all. They're not like planetary nebulas that come in all these different forms and colors, and open clusters or nebulas that have all these different shapes. Globular clusters are these globes of stars, but as we'll see, they've actually got different characteristics and morphology that make them interesting and fascinating. Plus, they're really accessible to people. So because they're stars, they're dense, they have high surface brightness, and they're really observable quite easily. Unaided eyes, naked eyes in rural locations, cottage, and so on. If you know where to look, you can find them in the sky just by looking up for them. Binoculars, they become real easy to find from a dark site. But any size telescope will let you look at globular clusters, and they're even good from the suburbs. You might need go-to help if you're deep in the city, but as long as you can see a number of the semi-bright stars, there are always a number of globular clusters that will help you locate and look at. So I thought that would be a great thing to look at. Plus, summer is globular season in Canada. We'll come back to a bit of that in a bit. So what I thought I'd do is I'm going to share my screen here and bring up Stellarium. Actually got a couple of neat things to show today. Let me just see if we can bring up Stellarium here. So what I'm starting off with here is this beauty. This is Omega Centauri. Now we can't see this from Canada, although theoretically you could get in the car and drive south for not too long before you could sort of see it peak above the horizon. This is basically the biggest, brightest globular cluster in the sky. It's visible really well from the tropics in the southern hemisphere. And it's a naked eye object. And so people have, when you talk about who discovered globular clusters, well, everybody did, because anybody who saw this fuzzy object in the night sky from antiquity has seen a globular cluster. So that's kind of like number one on the list. Everybody's seen that one. But after that, we started getting into the early explorers of the night sky using the telescopes. People like Halley and Lecaille and Messier, they were scanning the skies looking for what's up there with their newfangled telescopes that had recently been developed. And Messier, of course, was looking for fuzzy things that moved and getting annoyed by the fuzzy things that didn't, because they weren't comets. And so he started tabulating them into his Messier list of deep sky objects. So Halley was working around 1677, Lecaille in 1751, Messier in 1764, kind of all in that range. And between them, they found about 34 globular clusters visible from, the mid-northern latitudes. Now, they didn't know what they were. They were just calling them nebulous or fuzzy objects. Then around 1780 to 1800, in that range, we got William Herschel using his big scope. So he was using a set of different telescopes. He had a 6-inch diameter, a 12-inch diameter, and an 18-inch diameter. He was calling them, 20-foot, his 20-foot telescope, referring to its focal length, to systematically map the sky. And then he encountered a number of them as well. So he picked up another 36 globular clusters. So at that point, he was starting to resolve them, resolve what they were, and being able to tell that they were made of conglomerations of stars. So he coined the phrase globular star cluster. As we got into the 20th century, we started working a little bit more with astrophysics and more scientific, more rigorous numerical scientific analysis of astronomy. And a gentleman named Harlow Shapley at Harvard University started analyzing globular clusters. And he had access to photographic plates and bigger telescopes, and was determining that there were actually variable stars in globular clusters, the same variable stars that one had discovered in the regular night sky. And so he started to take advantage of that, period luminosity relationship that Henrietta Swan Leavitt had developed to estimate how far away those variable stars in the globular clusters were, and therefore how far away they must be. And that introduced some interesting ideas. So everybody was trying to figure out, how big is the universe, how big is the galaxy? And he assumed that the variable stars were Cepheid variable stars. But actually, it turned out that they weren't. They were actually a different type called RR Lyrae variable stars. But nevertheless, he used the Cepheid variable relationship and plotted them, noting where they were on the sky, on the celestial sphere, and then how far away they must be. He kind of developed a model of where the sun was compared to, the rest of these globular clusters, and eventually deduced the kind of layout of our galaxy, that there was a galactic core, and that these globular clusters seemed to be distributed around the galactic core. I'll come back and show you a really cool app that'll show that here in a minute. So he actually estimated that the center of our galaxy was about 60,000 light years away, but he was out by a factor of about 2, just because he was using a different type of star than he thought he was. So, the true number is about 28,000, our distance of the sun from the center of our galaxy. So what I'm going to do is I'm going to come back to home base here in Stellarium. Let's get this up here. Go back to default location. And I'm going to bring up the night sky and show you how things lay out. So let's go into the evening. Let's go to about 11 o'clock, once it's nice and dark around 11 o'clock tonight in Toronto. And we'll bring up the Messier objects here. So what I'm doing in Stellarium is I'm going into the DSO, the Deep Sky Object Catalog, and I'm enabling the Messiers, the NGCs, and the ICs, but then I'm filtering, switch on this filter, and only showing the globular clusters, and then revealing their labels and markers. And so you can see a number of them scattered around the sky. And I'm just going to turn off the daylight here just to make the sky nice and dark. And you can see already that we've got a number of them visible kind of in this zone, which is near the Milky Way. And of course, the center of our Milky Way galaxy is actually sitting here near the Teapot of Sagittarius. I'm just going to advance to midnight and bring it up. And you can see this plus GC, that's the positional coordinate of our galactic center, the center of the Milky Way galaxy. And so you can see that there's a number of these globular clusters scattered through Scorpius and Sagittarius and Ophiuchus. And it turns out that if you actually hide the ground and pull back, you can see that all of this zone around away from the center of our galaxy is devoid of the globular clusters. There's only a couple of little stragglers at great distances. It turns out that most of them are actually within, within about 90 degrees of angular degrees of sky from the galactic center. And that gave him the idea that these must be kind of swarming, distributed around the center of our galaxy. I'll come back to that in a second. His student, one of his students at Harvard was Helen Sawyer Hogg, who later married Frank Hogg and immigrated to Canada and worked at the Dominion Astrophysical Observatory on the West Coast, and then eventually ended up at the David Dunlap Observatory. And so she took on globular clusters as her specialty, did a lot of research on them. So by 1947, she had accumulated a catalog or a list of 99 of them, but only 97 of them were actually genuine globular clusters. There was some confusion about what they were at that point. By 1959, she'd expanded that to 118. Again, only 115 of those were actual true ones. And then over time, the ensuing decades, we had other researchers, people like Halton Arp, Kenneth Glyn Jones, Malott, you may have heard of, has produced a catalog of open clusters. And Helen Sawyer Hogg's student at University of Toronto, who was my professor when I went to U of T for astronomy, Christine Clement, who has carried on the legacy of globular cluster studies, they eventually came up with about 157 globular clusters that belong to the Milky Way galaxy. And that list, there's a list of them that's been tabulated by Professor Harris, William Harris at McMaster University, and he hosts a website with lists all of the numerical parameters for the Milky Way's globular clusters. I think Samantha's put the link in the chat for you guys. And that's kind of, it takes a few minutes to kind of understand what all the various parameters that he's describing or sharing. But, when you start understanding, which columns of numbers mean brightness, which ones mean diameter, all these different things, then you can start to go through them and pick out which ones are the biggest and best and brightest and so on. Now, of course, in modern astronomy, we've discovered globular clusters elsewhere, and now we're finding that most of the major galaxies have their own set of globular clusters. I think we've discovered upwards of, a couple of hundred, several hundred around the Andromeda galaxy, of course, which we have a very good view of. And then up to 13,000 globular clusters around Messier 87. So that's the one with the supermassive black hole. And we'll come back to this in a little bit, but one of the mysteries about globular clusters is how they formed. And one of the prevailing theories is maybe they're created by some process or other during galaxy merger. And so, we think that M87 being this big elliptical galaxy has probably swallowed up a lot of junior galaxies to produce its current form. So maybe those processes have created a lot of those many, many thousands of globulars. around.
So I have a couple questions. So we can actually see globular clusters in other galaxies, or are
Yes.
these just, so that's really cool, because what I've heard is all the individual stars like that you can pick up is all within our own Milky Way. So to have that much detail in other galaxies, just they must be pretty bright objects, pretty significant objects then.
Yeah, well, I mean, we're at the point where with our largest aperture telescopes, we can resolve down to individual stars in some of them closer galaxies. So the Andromeda galaxy, we can analyze, we can look for the individual variable stars in other galaxies. That's one of the reasons that one of the mechanisms we use to calculate how far away galaxies are is by identifying their Cepheid variables, or there are Lyrae variable stars in them, just by taking pictures of them over time and seeing which stars within them get brighter and dimmer and cycle over time. So yeah, the big telescopes, they're able to really focus in and see the details of these galaxies that it's just not part of our everyday experience with our backyard telescopes, or even our big reflector telescopes.
So no chance of me seeing a globular cluster in M31 in my backyard then.
Sorry?
No chance of seeing the globular clusters in M31 in my backyard.
You might be able to. Actually, if anybody has Sky Safari app, you can actually zoom in on M31, and you'll see all the other little NGC objects or globular clusters around M31 plotted in Sky Safari. So you might be able to identify them. So definitely there are rascals watching that have imaged M31, and I'm sure they could go through and plate solve and figure out which of those little smudges are the globular clusters.
And another question before we go on, just you've talked about we see a lot near the core of the Milky Way. There's a lot of globular clusters. Is this the time to look at the Milky Way from where we are, if we're going to get the best view of it? Would be this time of year as well?
Yeah, so this is why I said summer is globular season. So here, let me just put here's tonight's sky at midnight, and already you can see that a number of the globular clusters are all the ones that I'm displaying. All the yellow circles I'm displaying are only globular clusters. That's at midnight. And of course, if I advance into July, so let's jump ahead a month, or even into August, we can see that in late evening in July and August, we've got quite a few globular clusters available. The majority of them that we can see are in the summertime sky. So yeah, that's one thing Helen Sawyer Hogg used to do, is she would use the David Dunlap Observatory telescope, all-nighters, because the nights are short in the summertime, but that's when her beloved globular clusters were available. So she would spend all those clear nights, imaging them, taking plates.
And go back to our episode of the tour of the David Dunlap Observatory, where we talk about.
They are available at other times of the year, but summer is all right. So let me show you this other app that I was mentioning. Let's see if I can bring it up here. So this app is called Our Galaxy. It's written by a gentleman named Bill Toomey. He was part of the team that created Sky Safari back in the day. And he asked me to review this app for him a while back. And I finally, I've done that, and I realized that it's available on my MacBook. So I'm showing it on my MacBook here. It's a free app that you can download on your iOS devices. I don't think it's available for Windows or Android yet. I'm not sure. But what it is, it's a 3D model of our galaxy and the deep sky objects within it. And so what you can do is you can pull back here and then roll the galaxy around in 3D. And what you're seeing here are all of the Messier objects plotted in their correct 3D locations. So you can see there's the sun's labeled here. So you have a large mass of Messier objects in the neighborhood of the sun. And this will be things like open clusters and some of the bigger and brighter nebulas and things like that. And the ones that are more farther afield are the globular clusters. So what I'm going to do is I'm going to switch the set here. So if I click down here, I can ask for globular clusters, all of those. And now this is a plot of all the globular clusters that we have in the Milky Way galaxy. There's only about 29 globular clusters in Messier's list. But as I said, there are about 157 or so that are known to belong to the Milky Way galaxy. So you can see it if I pull out, some of them are extremely far away from the galaxy. And what's happening here is that globular clusters are these very ancient accumulations of hundreds of thousands to maybe a million stars. The stars are generally considered to be population 2 stars, which are low metal. What that means is that they're dominantly composed of hydrogen and helium and deficient in the heavier elements. So the stars that we normally see in the night sky, they evolved later on in the lifetime of the universe, after there have been time for heavier elements to be synthesized in star interiors and supernova explosions and things like that. Well, stars like our sun have mainly hydrogen and helium, but lots of other heavier elements. And of course, the heavier elements that were part of our protostellar cloud got incorporated into the rocky planets and things like that, the iron and the platinum and all the other uranium heavy elements. But the stars that were made or that populate these globular clusters tend to be these very primordial stars that were formed way back before the universe had much time to create the heavier elements. And so they're called low metal stars. Now their shape is generally spherical or oblate, so they can be kind of oval a little bit if you want, but most of them are kind of round in shape. And they're all bound together by mutual gravitation, and we'll talk a little bit later about why they don't just collapse on each other. A couple other neat things about globular clusters: they don't have any interstellar gas inside them. So we think that either all of that combined solar wind from all those stars all grouped together has blown all the free gas out, or maybe it's just all been swallowed up or used into creating stars. The age is around 13.5 billion years, plus or minus a couple of billion years. But there are a few known to be younger, maybe even half that age, maybe 8 billion years or so. And what we think is that the oldest ones are the original ones in our Milky Way's family, if you like, and then the younger ones might be captured. So they may have been created in a different galaxy or dwarf galaxy and then captured by our Milky Way. What else is cool about them? They have a very high fraction. So if you look at a typical population of stars in the nighttime sky and compare that population with the stars in a globular cluster, there's about 100 times the typical amount of white dwarfs and neutron stars. And that's partly because that's, a lot to do with the fact that they're so ancient. So all the, many of the stars have gone through their life cycles and ended up as the end product, which is a white dwarf or a neutron star. Black holes is another matter. It's very hard to find a black hole inside a globular cluster because it's so dense. But we have found a couple of globular clusters that are known to have intermediate sized black holes in them. But maybe with James Webb Space Telescope and some of the bigger 30-meter telescopes that are about to be brought into service, maybe we'll be able to peer more deeply into the center.
We have,
go ahead.
Oh, sorry. Question about globular clusters. A couple things. One, this app that you are using, thanks to the sleuths in the chat, it is actually available on all platforms now. It's called Our Galaxy, and I put a link into the chat. So yay for Windows people. We're not left out anymore, and Android. Another two questions we have: are globular clusters in the process of collapsing into their core because of gravity? Do we know that?
Sorry, say that one more time.
Are globular clusters in the process of collapsing into their core because of gravity?
So that's what we're going to talk about towards the end. But
okay, I will
maybe kind of, sort of. Yeah.
We'll lead that into. So Phil, Your question's going to be answered coming up. And another one, are there any exoplanets in globular clusters?
So the answer seems to be no. So for a couple of different reasons. So number one, there wasn't any heavier elements around to produce planets, the way I just mentioned the terrestrial planets we have here on Earth. It seems like the gravitational dynamics inside a globular cluster might tend to eject a planet or might tend to absorb it. So if you had, say, a Jupiter-style planet or a gas or an ice giant planet, it might be more likely that it just gets sucked into a passing star rather than, be able to exist for a period of time. So we haven't found any planets around any stars in globular clusters. But then, with these new tools we're bringing online, maybe we shouldn't shut the door on that idea. So maybe we'll find them, but doesn't seem so. Yeah.
Thank you.
Okay, a couple other things to look at here. Let me just bring you this web browser page here. This is just a diagram from Harlow Shapley's paper showing how he schematically plotted the plane of our galaxy and then plotted the distribution of the globular clusters. But one of the things I wanted to show you is the Hertzsprung-Russell diagram. So an HR, a Hertzsprung-Russell diagram, is a tool that astronomers use to classify stars based on their brightness and their temperature / color, that sort of thing. And you find that various populations of stars fall in these different categories. And most stars live on the main sequence. So on the main sequence, you've got at the left-hand side of this graph, the hottest stars. These would be your blue-white stars like Sirius and the stars of Orion's Belt and the summer triangle stars, O and B type stars. And then in the middle, you've got your sun. There's a sun labeled here, a yellowish star. And then you get your reddish cooler stars. So the cooler stars are dimmer and they tend to be smaller and they have lower temperatures. So temperature is high at this side and low at this side, sort of flip from what you might think. Here are the letters up here, O, B, A, F, G, K, M that we use. And this is a typical population of stars. So you have your main sequence. And then when stars begin to evolve towards the end of their lives, they start moving off the main sequence and populating these other zones up here. So you get your red giants, your supergiants. Those are the ones that have, expanded in the process of cooling and expanding and things like that. And then when they ultimately die and they blow off their outer shells and leave their exposed cores, then you end up with the white dwarf stars, which are hot. So they're on the left side of the graph, and they're smaller and not as bright. So they tend to be near the bottom left corner of the graph. So this is a graph of typical family of stars, just in the galaxy. But then you get globular clusters. It's a little bit formatted a little bit differently, but you can see that the main sequence here takes a jog to the upper right. And what's happening here is that the stars are all kind of evolving at the same rate. And so as a group, so these are all individual spectrum of the stars within a particular globular cluster, Messier 3. And there are a batch of them that are still on the main sequence, and then a whole batch of them that have been evolved off the main sequence into that red giant zone I was talking about. And there's hardly anything sitting over here on the left-hand side. And that's because the hot stars live fast and die young. And because the globular clusters are so ancient, the O and B stars have all lived and died and gone. And so most of the population of the cluster is the sort of F and G stars and down to the red zone. So it's actually true that spectrally, a lot of globular clusters kind of, as a mass, come into the sort of F and G kind of a color to them. So they're kind of a reddish color, less blue color for globular clusters. A couple other interesting things. There are some blue stars inside globular clusters, though. We'll come back to what those are in a little bit here. Let's bring up my Stellarium again. So what else? So obviously they're very dense. They're all sort of compact. A typical density for a globular cluster would be about 0.4 stars per cubic parsec. And a parsec is 3.2 light years. So you can do the math. I'll come back to that in a sec. That's on average, but in the center, you can get 100 to 1,000 stars per cubic parsec. So they're actually, a few hundred astronomical units apart. For us, the nearest star to our sun is 4 light years away. So that translates to a bulk spacing of about 1 light year between stars in the center, on average, and about 0.3 light years between stars in the core of the globular clusters. So it's, there's room in there, but it is really, really dense. And again, Samantha, just interrupt me whenever you need to.
No worries. I will interrupt you in questions. Feel free, as always, Q&A or asking in the chat. We're monitoring both.
So we're not sure, as I said, we're not sure how they form exactly. It may be that they form in a similar way to open clusters, in the sense that a collapsing cloud coalesces a bunch of stars inside that cloud, and generally there's some kind of angular momentum or rotation to that group of stars initially, and maybe globular clusters were formed from some sort of supercloud. But what is true is that over time, over their lifetime, they've actually stopped rotating. So the globular clusters tend to have no bulk rotation to them. They're just very sort of static, and instead they're doing so much more random motion of the stars inside. As I said, most of the globular clusters in our galaxy are all around the same age. The population of the stars, when you sort of make those HR diagrams out of them, you do find families of stars. So they're not completely homogeneous. You get maybe a couple of different generations of population stars in a globular cluster. So it's not purely one. You can get 2 or 3 different populations, as if there was an initial set of stars formed and then something else later triggered another batch of star formation. And so you get these different sets. I talked about the metals. So they have about 1% of the typical heavier elements that a star like our sun would have. Okay, so let's talk a little bit about the blue stars I mentioned. So the one weird thing you can find inside globular clusters are something called blue straggler stars. And these are kind of ultra massive, bright blue stars. And we think what causes them are stars merging, because everything's so packed together inside the globular cluster that we think the stars can actually either pair up or coalesce. And when they coalesce, you can get these, double the mass and then kick up the fusion and produce these hot blue straggler stars. So those are things that you might read about if you do some research into that. The other neat thing is that because we have the globular clusters are kind of orbiting around the center of our galaxy, they're actually in the eccentricities of their orbits vary. You can actually have globular clusters dip in or dip through the plane of our binocular galaxy, sort of pass through the plane, go up, stop at the top, go down at the bottom, and so on. And when they pass through the plane of the galaxy, they can actually potentially pick up gas, and that may trigger some subsequent star formation. So you can have different things. Also, you can get gravitational effects where a globular cluster that's passed through the plane of the galaxy actually may have actually had some of its stars drawn off of it by the gravitational pull of the galaxy. So you get some of these, hairy strands of stars on the outside of it. All right, so let's talk a little bit about their sizes, things like that. So
we have a couple questions. Sorry.
Okay. Sure.
One is, are all the stars in the globular clusters rotating in the same direction?
No. And that's one of the reasons they don't collapse. So we'll definitely come back to that. Good question.
And the other one is more of a thought experiment, I would think. Imagine if we were in a planet in a globular cluster, in this globular cluster, would the sky brightness, would they even have a nighttime? Or are they that packed?
Yeah, probably not. So it sparks the imagination. I'm sure there have been more than one science fiction story or novel written about life inside of a globular cluster, although we don't think there are any planets. So too bad about that. But if there were, that would be really neat. So for example, years ago, astronomers used the Arecibo radio telescope to beam a message to M13. So if there's anybody living, if there's a globular empire civilization inside the M13, imagine how easy it would be to visit your neighbors, right? A fraction of a light year away, if you could do it. You wouldn't necessarily even need faster than light travel in a situation like that. But yeah, it would be bright in there for sure, and lots of radiation. One of the things that is neat about globular clusters is that the stars that have extinguished and have become white dwarfs and neutron stars, they're a high source of X-rays. So there's lots of X-rays coming out of globular clusters. So it's probably not very friendly to biological life. But yeah, so we beamed a message to M13, but it's going to take, where's the number here? Find M13. So it'll take 25,000 years for the message to get there. So that's the one downside of that idea. All right. Any other questions?
25,000 years for them to get back to us.
Yeah, 50,000 years.
Maybe put a couple years for them to figure out how to transmit back to us.
That's right. The good news is that when we get to our Globie Awards, there are some much closer ones. So we'll talk about that when we get down there. All right, yeah. So let's talk about a little bit about how they look and how we deal with that. Let's make sure I got my stars showing here. Yes, I do. Good. Let's turn off this symbol just so we can get some look at them. So we can measure their angular distance in the sky. We can see how many arc minutes they span. And of course, you've got to think about what defines the edge, because they tend to be a little fuzzy edge. But I mean, typically they can be anywhere from 10 arc minutes to 50 arc minutes across. So 50 would be nearly twice the diameter of the moon. Then we use other more scientific or more numerical techniques for measuring the size of them. We use something called the core radius. And the core radius is the distance at which the luminosity drops by half. So if the globular cluster is very concentrated in the middle, then that radius will be small. And if it's very more diffuse, then that radius will be greater, because it takes more distance before the light drops by half. There's also a parameter called the half-light radius, and that's the distance. That's the distance from the core containing half the luminosity of the cluster. It's a little bit of a distinction between them. It tends to be a little bit larger number than the core radius. Typically, that's about 32 light years, give or take. So that's the half-light radius. Now, the problem with the half-light radius measurement is you're using sort of photometry to look at the brightness of the cluster, but you're not factoring in the fact that half of the this hemisphere of the cluster stars are in our line of sight. So we're not just seeing the core stars, we're actually seeing part of the halo that's on this side of the cluster from us. And so we do a correction to kind of remove those, and they call that the half mass radius. That takes that into account. And then you've got another concept called the tidal radius, or the Roche limit, or the Hill radius. And that's essentially the gravitational influence of the cluster. So where does a star how far away do you need to be from the core before you're feeling the pull of the neighboring star more than the stars of your home cluster? So at some point, you kind of call that the sphere of influence, or the tidal radius. So you'll notice that if you look at something like M13, let me just bring up M13 here. But one of the things you'll notice if you look at M13 in the telescope is you will see, a ragged edge, and you'll see streams of stars that may have been sort of pulled out of it either through a passage through the disk or from some other encounter. But bottom line, most globular clusters are around between 100 and 300 light years in diameter. So M13 is mid-size. It's about 145. Questions? No? We're good? So as I said, about 90% of the Milky Way's family of clusters are within 90 degrees of the center of our galaxy, sort of near the Teapot of Sagittarius. About 10% of them are farther afield, including the Intergalactic Wanderer. I'm not sure if I've got the Intergalactic Wanderer in my list here or not, but that's okay. And there's one in Lepus. So if I bring up the winter sky here, let's go back a few months. There we go. So there's a globular cluster in Lepus, M79, and it's actually 124 degrees away. So it's nearly on the opposite side of the sky from the galactic center. And again, some of these might be globulars that have been captured from other galaxies. So the bottom line is Sagittarius has 35 globular clusters, Ophiuchus has 33, and that's why the summer is globular season. So as I said, they're orbiting the center of our galaxy in a very eccentric orbits. The orbits can be several hundred thousand light years in radius. So they can really travel far from the sun, from the center of the galaxy. They're often moving at high relative velocities to our sun, so either moving towards or away from us. And let's see, what else do I have? A lot of them are moving every which way. So you can have prograde orbits and then oddballs that are running retrograde. And so, you know, the Milky Way has this bulk rotational sense, and you could have globulars that are kind of running counter to that. And those we think also might be the captured ones.
Do we have a mass plot of globular clusters? Like, have we plotted the mass of various globular clusters?
Yeah, so if you pick one, so let's pick one here. So I'm not sure if it gives me the solar masses here, but there's a list. I gave you a link to the list.
Yep, I sent the one with the 157 Milky Way globular clusters.
Yeah, there's one. So Wikipedia actually has a list of globular clusters. Let's see if it's open this one. Yeah. So I think this one actually has the, no, it doesn't have the solar masses, but you can actually find that. Off the top of my head, I don't happen to remember what they are.
So it exists, but you might have to do a little bit of digging.
Yeah.
So
definitely not missed by Dr. Harris. He has them in his list as well.
So that was the list I shared first at the beginning. That's everything for now.
All right. So let's see. Let's talk a little bit about how they look. So globular clusters, you know, as I said, at first thought, you might think they all look the same, but really they don't. There's actually a difference. And that's because the idea of them collapsing after they've been formed actually causes, in some cases, the cores to be more concentrated and the halos to be more diffuse, or they can be uncollapsed, in which case they're all rather diffuse. You know, you can resolve the stars in the center fairly easily. The ones where the cores have collapsed are so dense that we can't really resolve individual stars when we look into the center. So I'll give you a couple of examples here. Let's see, how about M75? So M75, I'm just going to hide the ground and zoom in. I'm just going to use the Stellarium deep sky survey image here. So you can see when you look at M75, you've got a very intense core to it. And then the halo doesn't actually, expand too far beyond. So this one is well along this process of collapsing the core. As opposed to Messier 4, which is in Scorpius. And this one has an uncollapsed core. And in this case, you'll be able to notice. See how you can see the space between the stars, even as you get towards the middle of the cluster. So it's much more gradational. So when we talk about when you look at our Messier minutes in a little bit, that's one of the things you're going to maybe mention in your logbook is, did it look like it was, concentrated? Did it look like it was more uniformly distributed of light, or, what was the sort of density profile? How about a very dense one that's not had its core collapse? That's M13. So you can see it's very, very dense in the middle, but we can resolve stars in Hubble images and other high-res images. We can see the core quite well. And then a not dense and not collapsed is M55. This one you'll see a really big difference. So look at the difference. It's really amazing how you can see that. And you'll be able to see that in your backyard telescope. You don't need a big telescope to see the morphology, the characteristics between these two different types. So let's talk a little bit about the concept of the globular cluster collapsing or not collapsing. It's a little tricky and mind-bending, but we'll get through it. And we've got a couple of links that you can take your time to look at as well. So, as I said, the clusters themselves are not rotating now, but they may have when they were first created. But what does happen is that the stars inside the cluster, their motions have become randomized. And that's mainly because they can barely go around the corner without bumping into another star and either, getting deflected by it or disrupted by some way. So any star that, sets up a regular orbital motion finds itself deflected before long, and it can be deflected into the center of the cluster or out, or just change its lateral direction, that kind of thing. And so the effect of that is that eventually the stars act a little bit like just bees buzzing. They're just basically just almost like the atoms in a gas, which are just sort of not going anywhere particularly, but are just sort of bouncing around. Now, of course, in a gas, you've got molecular forces that are causing atoms to bounce off each other and things like that. Well, we don't have that in a globular cluster. What do we have? Well, it's mainly to do with momentum transfer and stars, being flung here and there over time. So basically, it takes, once the cluster is formed, astronomers think it takes between 100,000 to 1 million years for any particular star to cross the diameter, across the center of the cluster. So there's plenty of time for stars to buzz around and move around the cluster over these 12 billion year plus lifetime. Now, you'd think that the heavier stars would want to fall inward, but they don't, because there are actually processes that are keeping them inflated. And one of the terms you'll find is gravikinetic energy. So the jostling of all these stars interacting gravitationally is kind of putting energy into the center of the core that kind of keeps it inflating. So there's nothing to sort of relax and just collapse. So it kind of keeps it inflated. You can, though, get mass differentiation. So you will find that the heavy stars want to fall to the center. And as they do that, they're going to encounter lighter stars. And generally the heavier star will give up some of its kinetic energy, some of its speed to the lighter mass star, and add some speed to that lighter mass star. And that can tend to throw the lighter stars more to the halo, more outside, while the heavier stars kind of dropped inward. But the trick here is that one of the other neat things about the density of the cluster is that it's highly likely that binary pairs form. So stars, encounter one another and then hook up, and you get these binary pairs forming. And the binary pairs act almost like springs. So when a third party comes into the binary pair, it's going to trade energy with the binary pair. The binary pair may give up some of their kinetic energy to that third star, send it on its way, and maybe their orbit will close up a little bit. They'll speed up and orbit a little bit faster. And so you get a process where a lot of these binary pairs are kind of doing this in the center of the core and keeping it, inflated. So it's kind of like the isostatic equilibrium idea of a star not collapsing because there's so much energy happening in the core. You get these gravimetric or gravikinetic processes in the center that just keep things from coalescing, that just keeps things inflated. Now, what's interesting though, is that you'll find that globular clusters can plateau. They can collapse for a point, and then they reach kind of a stasis, where they can stay that way a while. There are processes where the binary pairs can then start kind of relaxing and giving up more energy, and that extra energy they release actually causes the core to inflate or swell up. And so you'd think of that as the core uncollapsing. And so what we're wondering now is when we look at these different types of globular clusters that I've just shown you examples of, maybe we're actually seeing different points in time of a oscillatory behavior. So maybe the one that doesn't look collapsed is currently inflated, and we see one that looks more concentrated. It's because it's had its core collapse, but later it may eventually expand and relax again. So that's what's neat about astronomy, is that we're discovering new things all the time. And maybe by the time some young person watching today has followed the science for a while, they'll have it understood and they'll know some other story. But that's kind of the story it is right now. So let's see, what else have we got here? Talked about the planets not being likely.
We do have a question.
Sure.
If you can go in more detail why the planets aren't necessarily likely, because they're asking, is there any part of that process actually happening there and then just gets stopped somehow?
Part of the which process?
Planet forming process. So we talked about planets not being able to form because they'd be ripped apart. But is there any element of planet forming process we think happening in the globular clusters?
Right. So, we know that there are stars inside the cluster that exhaust their fuel and blow off their skins, blow off their shells, turn into white dwarfs, etc. So they are seeding the cluster with material, with a slightly heavier elements. It's hard to imagine a star finding its own kind of corner where it can form its nice photostellar disk without being disrupted by a passing bee, right? There's so much activity going on inside the cluster that it's unlikely that there's time for the protostellar disks to coalesce and for the planets to form. So, something will pass by and it'll steal the disk off the star, that kind of thing. So I think that's really the matter of it, is that it's so chaotic and so dense that you just don't have that space and time to form. Hopefully that.
We also had another question about, and I asked if they could elaborate a little bit more on it. Where did it go? If general relativity is acting in globular clusters, and I could say for sure, because there's so much gravity, and there's no way it's not acting there. But if you want to elaborate, the person who asked that question, if you have more of a specific question and maybe in what manner. But in all these cases, we're talking about, other than just our day-to-day lives of throwing a ball and catching with our friends, general relativity is the main theory of gravity that we use at these large scales.
Part of it's going to be, do things start moving fast enough in order to bring in special relativity and other concepts. And it doesn't seem so at things that, the clusters, the stars in the cluster are kind of jostling, but they're not really speeding around that much. I don't think we're getting into kind of, there may be, and as I said, there may be black holes in the center of some of these clusters, so you'll certainly get relativistic effects that are happening around the black hole event horizon. But I think that's an area of science we just don't know that much about yet, because we've not had the tools to really, cut them open and see inside them as well as we'd like to. So yeah.
I think there in general, we're still refining our theory of gravity and how things work with dark energy and dark matter and quantum. So we don't know fully.
So let me show you this this classification scheme here. See if I can do this for you. So back in 1927-29, Shapley and Hogg created the classification system that's really strictly visual, so how they looked. And they were classifying how dense the core versus the halo appeared. So you can have really dense core, very faint halo, which would be at one end. So that would be the most dense. And then you could have the core not being very much concentrated at all. So that would be a very least dense. So the most concentrated core, globular, in the Messier list is M75. I think I showed you this one already. That's a very...
It's linked in the chat, this table you're talking about, so people want to follow
then from there, we can go to M80. So this is be a class 1. And when you're using Stellarium, you'll see that it tells you right here. So M80 type globular cluster bracket, Roman numeral 2. So this would be intermediate, number 2. M54 is the third one. And I won't go through every one, but we get a sense of this. Let this load up. There we go. Somewhere in between, you're seeing that the core is a little brighter and the halo is a little bit less. And then M3 is kind of class 6. That's kind of in the middle of the range. And again, we're not talking about the diameter here, the size. You're seeing different sizes here just because some of these are bigger and smaller in the sky. But that's kind of an intermediate. So that's your sort of classic, typical globular cluster appearance. And then at the bottom end of the scale was that M55 that I showed you a while ago. So M55, really beautiful. So you can really see spaces within the stars all the way through the core of the galaxy. And I put a link in the notes that Tenho Tuomi actually produced a gallery of globular clusters that is very nice that you can take a look at. All right, so let's hand out some awards. First of all, let me show you what I'm doing here with Stellarium, just so you can emulate this if you wanted to. So this is a tool called, down here under astronomical calculations in Stellarium, F10. There's a tool that opens up and it's got a number of tabs, and you can work with eclipses and solar system positions and things like that. And this is the What's Up Tonight tab, WUT. And when you open this up, you've got different classes of objects that you can choose from. So I chose globular star clusters. I put a limiting magnitude. You want to put a limit on this so you don't get, many, many hundreds showing up. You just want the brightest ones. So this one's anything up to brightness of 9, so the brighter ones. And then when, so I said around midnight. So anything around midnight today, and this is the list you get. And there are, I think about 24 or so came up in this list. So it's kind of an easy way for me to show you these different objects that way. All right, so globular awards. So the best, brightest, the granddaddy of them all has got to be Omega Centauri. That's the one that everybody has seen since antiquity. So let's go to that one. And you can see I haven't changed the scale of the view here. So now this one's almost filling the screen. That's how big and bright it is. So you can't see it from Canada, but you could potentially, the highest it gets is around 11 p.m. in May 18th or so, is just below the horizon. It's only 1.5 degrees below the horizon, I think, at that time of the year for us in the latitude of Toronto. People who live south of Philadelphia, it'll peak above the horizon for them. And if you live in, say, Dallas or Atlanta, it rises 10 degrees above the horizon for you. And obviously, if you want to really see it in its splendor, you want to go to South America or Australia in late April, when it's nearly overhead in the sky. Just glorious, just majestic. So that's that. All right, so what about what can we see, Chris? So the brightest globular for us in Canada is M22. So that was, this one's magnitude 5.2. And what I'm going to do is I'm going to go back to the regular view here, and I'll show you where it is. So here we are at the Teapot of Sagittarius. Let me just bring up the sky on the ground here. And we'll go on later at night. The reason that the sky is kind of washed out is because there's a moon up. I'm just going to get rid of the moon. Here we go. Let's get rid of the moon. So towards later in the month, when we get into third quarter moon, it'll be a little bit more visible for us. And I'll bring back my stars here. Starting. So there's your Teapot of Sagittarius. This is where M22 sits, just above the peak of the teapot. And it's only, let's see, a couple of finger widths to the left of the spout of the teapot in Sagittarius. That's the brightest one in Canada, for Canadians, is about magnitude 5.2. Now, it's actually should be brighter than that, but because it's near the plane of the Milky Way, it's actually being dimmed by the intervening gas and dust in the plane of the galaxy. So really, it should be brighter, but that's what we get. The ones after that would be things like M4. So M4 is over in Scorpius, near the star Antares. So M4 is nearly as bright. And then M5 and then M13 up in Hercules. Those are the brightest ones for us. Which one is the brightest in the eyepiece, the largest in the eyepiece? The Globie Award for largest in the eyepiece for Canadians, and that's M4. So let's see if I can bring up the eyepiece view here. So there you go. So this is a 26 millimeter Plossl eyepiece and a 6-inch Dobsonian reflector telescope. But you can see that it takes up, kind of a quarter of the field of view. So that's kind of a nice one to look for. So that's kind of your largest in the view. It's 26 arc minutes across, so nearly as wide as the full moon. The closest globular cluster to the Earth is FSR 584. So it's not a bright one at all that we're familiar with in our, stargazing. It's only 4,600 light years away from the sun. It's the 160th globular cluster. So I mentioned there were 157 kind of formally recognized, and this is one of the candidates for expanding the list a little bit. It was discovered in 2007. It's located on the edge of the Heart Nebula, just east of the star Struve 257. So let me see if I can find the Heart Nebula. I'll show you where it is. Wouldn't be that impressive, but it's so it's kind of in this little zone. Anyway, I can find it later. It's not something that you're going to go and look at too easily. And there's actually a link to a paper if you're interested to see that.
Which makes sense. If it took us so long to find it, it'd be harder for amateur astronomers to see through their telescopes. So.
It's actually about 60,000 light years above the galactic plane and descending through it. And it's about 3,000 light years farther from the center of the galaxy than we are. Let's go back. How about the closest kind of observable globular cluster for amateurs is M4, our friend M4. M4 is going to win all these prizes. It's like the Grammys where one person comes up with an armful of awards. M4 is going to be that one.
We need to hand it, I don't know, badges. If you could give the star. You give the stars gold stars. Okay, I'm done.
Yeah.
Sorry.
So M4 is only 7,176 light years away from the sun, from us. Now, while you're on stage, might as well give you another award. I'm giving this one the award for the easiest globular cluster to find, right? Because it's only a thumb's width to the right of Antares in Scorpius. So when you see Antares shining of an evening, just turn your gaze just slightly, thumb's width to the right, and you'll be able to pick up the fuzzy patch of M4, definitely in binoculars. Okay, so Samantha had a request for me, and that was how to find M13. So M13 is actually pretty easy to find as well. Let's head on up.
I mean, every time I go out, I don't know why, I just get very unlucky. And I've been told it's one of the best ones to look at. All
right. So here we go. Here's Hercules. You want to find Hercules, you need to, locate the summer triangle, Deneb, Vega, Altair is here. And Hercules is kind of between Vega and Arcturus. So Arcturus is really noticeable in the sky these days. And
Arcturus from the Big Dipper.
So Arcturus is the one that points to the Big Dipper, arcs to the Big Dipper. Yeah, yeah. The Big Dipper's in this view is above here. So once you found Hercules, you need to be able to see the keystone, the 4 stars in the corner of his body. And on summer evenings, facing kind of southeast, the wider edge will be to the top and the narrower edge will be to the bottom. So once you've got the 4, they're medium bright stars. They're not spectacular, but you can find those. Of the keystone, you want to look on the west, the right-hand side, start at the top corner and go down 1/3 of the way. Right here.
Mm-hmm.
And there's M13.
Question, and somebody just put this in the chat, and that it highlights exactly what I had issues with. Is it so high up in the sky, it actually starts to hurt to look at it without a diagonal. Do you have any advice for binocular users or very basic telescope users to actually viewing objects this high up? Like this high, I know it's high, but.
Well, if you're using binoculars, have a chaise, lay down. That's always a great idea. So just lay your head back and prop them over your eyes. If you're using a refractor, make your tripod legs longer so you're not having to crawl on the ground to look for the diagonal. Those are, it is what it is. The great thing is that, M13 is going to be with us for a while, and later in the summer, it's going to be kind of not high in the sky, but halfway up the sky, so you'll be able to sort of look at it then. Yeah. All right.
So I think, what globular cluster is in your background right now?
That should be M13 behind me, I think.
Okay. I wanted to guess it, but I wasn't sure.
Yeah.
Okay, keep going. Well, should we hand the award to them now, or?
Yeah, so let's go. Let's see, what else have I got awards here? The farthest one. So we talked about the closest and the largest. Let's talk about the easiest to find. The farthest easy to see one is M54. This is crazy. So M54 is here in the bottom of the teapot, and it's 87,000 light years away. Crazy. M13 was only 25,000. This one's 87,000 light years away. So that's really ancient starlight that you're looking at. You look at that one. That's the farthest. I gave the most spectacular for Canadians to M13 just because even though M4 is so big, it's less impressive because it's so low on the horizon and we're looking through so much of its atmosphere. Farthest from the galactic core, there's one that's called AM1 that's not really observable for amateurs, but it's 400,000 light years away from the galactic core. The most overrated globular cluster, in my opinion, is the Intergalactic Wanderer. So the intergalactic, whoops, let me just find it.
Didn't know stars could be overrated. This is an interesting
Well,
award ceremony.
I would put it, lower in my list. Intergalactic Wanderer, Intergalactic Tramp, both names work. It's actually Caldwell 25. So it's a nice little globular cluster. It's not particularly bright. It's magnitude 9. It's let's see, size-wise, it's only 4 arc minutes across. So we talked about M4 being 26 arc minutes across. This one's only 4 arc minutes across. So, but the thing is that it's actually a spring object. So it's something that you don't need to wait for the summertime for.
Is that why most people put it on their list then?
It's on, I think it's on the RASC finest NGC, maybe. I'm not sure. It's definitely in the Caldwell list. It's Caldwell 25. But it is in the list of non-Messier.
2419? Yeah,
NGC 2419. Okay, so the weirdest looking globular, the most curious looking one, is M19. And M19 almost looks almost comet-like when you're looking at it. Here, let me give the other view here. So you'll actually, if you pay close attention, to see it's not circular. So it's kind of an oblong shape. And the core is not in the middle. The core is actually offset to one side a little bit. It's almost comet-like when you're looking at it. So that would have really fooled Charles Messier. So that's NGC 6273 or Messier 19. And it's located here in between Antares and the bottom foot of Ophiuchus. It's actually part of our Messier minute, so we'll come back to this one.
So I guess a good tip for a lot of these globulars will be to start by identifying where Scorpius and the Teapot in Sagittarius are. Just like we taught you how to do Leo, now I can always recognize Leo in the sky. This is your assignment for this next month, is to find these ones in the sky. We have a couple questions about what would win the award for lowest from the horizon in the view of Toronto. So what is the lowest globular cluster that you can see on the horizon? Yeah,
so if you're doing your Messier certificate, you're going to find there are 3 Messiers tucked here in the bottom, several Messiers tucked into the bottom of a teapot, and these can be hard to see, right? So this is not part of the Messier list, but M55 is. So that's the one that's very diffuse that I showed you a little while ago, one of the least concentrated ones. So that means its surface brightness is a bit lower and it's a little more challenging. You might find you've got your telescope horizontal if you've got a big daub or something like that. I found that one challenging. This one is going to, at this time of the year, so if I go back to tonight, and I'm just going to turn off my, yeah, I got that turned off, good. So you're going to find that one culminates at 4 in the morning. So it's not really time for it yet. Give it another month or two, and then we can take a look at it. But that's a good question. We're going to find some of these are challenging. Let's see. So M55 is my award winner for the stars all the way down to the bottom award. That's the one where you can kind of see the spacing in the middle. And my last award is the best not a globular award. So the globular that doesn't look like a globular award, and that's M11. So that's the wild duck cluster.
I think you have one more award you didn't mention too after this one.
Yeah. Oh yeah, I have one more. Yeah. So this one you might think is a globular cluster, but it's actually an open cluster. So that's the wild duck cluster. Nice and bright, easy to see in the summertime. That's the wild duck. And the last one I had was the best non-globular or non-Messier globular. So, something that Messier should have included, but he didn't. And that's the snow globe in Bootes. That's 5466. Where's my 5466? I'll find it this way. Yeah. So this one is actually sitting here. Let's get this, yeah. Sitting here near M3, which is a bright one. And so it's up here to the, let's see, I think this is visible. Yeah, so this is visible in the western sky after sunset, even now. So you can still grab a couple in coma, M3, and then you can pick up NGC 5466. And it's not a bad globular cluster. You know, it should have been in the list, I think, but it got overlooked. So I'll give it an award for that. All right.
So
last
we
question.
have one question. Anybody has questions about globular clusters? What we've talked about so far, as we move on to our Messiers, where we're still going to talk about globulars. But the one we have right now is, do globular clusters have unique signatures and other wavelengths of electromagnetic radiation? Like, can we detect globular clusters by looking for specific EM wavelengths?
Not necessarily that would make them stick out like a sore thumb, but they tend to be X-ray emitters. They tend to have bulk spectra that are kind of in the F and G class family. But I think that's basically it. They're more of a visual object really than an exotic object, if you want to put it that way.
Thank you. So any questions about globulars before we move on to Messier minutes? Okay. And then with that, this is our beginning of our Messier minutes.
Right. So we're gonna repeat a little bit of what we said here because I've already touched on some of these the Messiers. So what we're focusing on for Messier minutes this time around is the more westerly of the summer objects that we're going to tackle first, and then we'll be back in a month, and then we'll get sort of deeper into the summer Messiers as we get farther in. So the first one we're going to look at is Messier 9, which is an Ophiuchus. So Ophiuchus is this sort of Dalek-shaped constellation that's sitting over the southeastern horizon in late evening nowadays, above the Milky Way. And M9 is kind of down in this leg that sticks down below this lowest star named Sabak. So M9, let's bring up the eyepiece view here. You can see it's, kind of smallish. So it's too small to be seen really in binoculars, but really any size of a telescope will work on it. It's quite low in the sky, so it's actually been dimmed a little bit because of that. And it's also been dimmed because it's relatively near the Milky Way. See how it sits just, in the galactic bulge sort of area? So that's the dust and gas in our galaxy has caused the globular to be dimmer than it really should be. It's about 25,800 light years away. And as I said, you can actually, if you can find the star Sabak, then it's about 3.5 degrees south of that. But the other way of doing it is to connect the star Chi Serpens and Antares. And you can see that M9 is sitting on that line. So you can sort of find that line and then drop a perpendicular below Sabak, and you should be able to pick it up if you're using binoculars or a low magnification eyepiece. When you're looking at it, see if you can notice that it's a bit squashed. It's not round. It's a little bit distorted that way. And there are also some other objects nearby. So there's another globular sitting just to the left of it here that you can pick up while you're in the neighborhood. There's another one. I think it's below. Yeah, there's a couple more around. So enjoy that. All right, next up, we have M10. Now the body of Ophiuchus has some nice big bright globulars inside, and M10 is on the center line. So if you look at the peak of his head and then the center of his body, make that imaginary line, M10 is kind of on that center line. M10 here is, you can see it's bigger already than the M9 was. It's 12 arc minutes in diameter. Its magnitude about 7.7 or so. Again, a little small, sorry, here we go, magnitude 6.4. It's can be seen with the unaided eyes if you're in a dark site with the moon not around bothering you. You can certainly see it in good binoculars. You can see it any size of a telescope. If you've got a bigger aperture, you can see that the halo extends beyond here. So a bigger aperture will let you see more of the fainter halo around it. It's about 14,400 light years away. And as I said, if you use the center line idea between Razelhaig and Sake, it's closer to the bottom than the top. Did I have any other tips for you? You can make a right angle. So if you find the corner of Ophiuchus, drop down to Sake, and then go 90 degrees by about the same distance, that's another trick you could use to pick it up. And you can look for whether it's symmetrical. You can look for patterns in the brighter stars. So you can actually pick up some chains and groups of stars in it as well. Next up is M12. M12 is its neighbor inside Ophiuchus. I'll bring up the view in the Dobsonian. You can see it's about the same size, but it's kind of more concentrated, a little bit brighter. So it's medium bright, medium sized, 16 arc minutes across. It's this is one's going to be visible in binoculars and any size of a telescope. You can actually share the view with M12. M10 and M12 will share the view in binoculars together at the same time. If you've got a bigger telescope, you can actually resolve nicely the stars in the halo and get quite deep into the core with a larger aperture telescope. So you get lots of benefits from that. Let's see. So to find it, what I suggest, so if you've already found M10, you can slew a little bit up west and see it there. Or I find it between Kappa, Ophiuchus, and Sake. So there's Kappa, Ophiuchus, and Sake. So that's this one here. So if you start at the bright star Centauri and go to the corner, it's on that corner line. So that's one way of doing it as well. Or you could drop another one from Kappa, this top corner, down through Sake. So it's kind of along the intersection of those various lines. You can do it that way. Let's see what else to look at. If you're going to look at it, so Stephen O'Meara claims that there's kind of a rocket ship-shaped asterism of stars nearby. I'm not sure what he means. Maybe he means this, but pay attention to that sort of thing when you're looking. All right, just a couple more here. M14 is up next. So M14 is on just outside the body of Ophiuchus. So M14, you can see it's brighter already, even though it's relatively small. It's fairly bright. It's 30,300 light years away. That's what makes its diameter rather small, but it has a lot of oomph to it. So binoculars, really, or any size of telescope should pick that one up, maybe even your unaided eyes. Now, interesting, the photographic plates taken by Helen Hogg in 1938 were later reviewed in the 60s, and they discovered a nova on that plate inside this globular cluster. And it's the first nova ever imaged. So that's kind of a neat one. Let's see. To find it, a couple of tricks you could use. So I've got it halfway between Razelhaig and Chi Serpens. So that star Chi Serpens that I mentioned a minute ago. You go up towards Razelhaig, it's halfway between those two stars. So if you can find those two stars, just aim halfway between them and you'll pick it up. When you're looking at it, also look for, there's a couple of other globulars. There's NGC 6366, a few degrees to the southwest, kind of in here. So you can take a look for that. All right, next up is M107. So M107 is down here below the body of Ophiuchus. And again, if you can find the star Sake, it's just a few degrees below that. So that's pretty easy. In a telescope, you can see it's pretty small. So it's more diffuse, less bright. So it's less bright, it's smaller. It's not really a binoculars object. But if you want to try for it, you want to try looking when it's highest in the sky, which is sort of after midnight. Let's see, it's for reference, it's sitting right above Antares. So that's kind of, you can look above Antares for sake and then find the star there. The surrounding stars form a crucifix. You can see there's a star here, star here, and then a couple stars here, and it makes a crucifix. And in a reflector telescope, those flip around. So the long arm of the crucifix will be up, down, inverted, like that. That's kind of a neat thing to look for. Again, so when you're looking at it, notice that its core density is less, and it's got a little more dimension to it that way. Okay, next up, M4. Our friend M4 that we got all the awards. So M4 is dead easy to find. It's just sitting here to the west of the star Antares. Huge, bright, not as concentrated, really easy to find. You can see it with your unaided eyes, especially when it's highest in the sky, so after midnight. Binoculars work, telescopes work. It's been reported that it has kind of an internal bar structure, maybe a shape to the core, and some chains of stars extending beyond it. So you can look for those sort of fuzzy fur around it. It's among the closest of the globular clusters. That's really an award-winning one. And M80, let's go with M80 here. M80 is above Antares and M4. And what's neat is that a few of these you can use the claw stars of Scorpius to find. So M80 is easy because if you go halfway from Antares to the highest claw star, A crab, it's halfway along. So that's an easy one to find. And again, it's really concentrated. See how bright it is? The M80 is medium bright. Any telescope will work. Really dense, 32,000 light years away. And make note of that density gradient. We're looking for it. And also, you can be, and while you're in that neighborhood, you can look for the Rho Ophiuchi reflection nebula complex sitting to the lower left. M19. Where's M19? Here we go. M19 is here. M19 you can find by taking the lowest claw star named Fang and doubling its line through Antares, and that'll put you right on M19. So that's easy. This one is a bit more diffuse, a little fainter. So it's large, but it's faint, and it's also been dimmed by the galactic dust and gas. If you're going to try it in binoculars, wait until it's higher in the sky, it's sort of 1 a.m.-ish. And if you've got a bigger aperture telescope, you can pick up lots of neat details, patterns of stars, and resolve the core, which is really nice. This is also the one that's got the outer round shape and the comet-like shape. So the center of the core is offset from the center of it. And there are other globular clusters nearby. There's one little smaller one here and a little smaller one here, all within a couple of 1.5 degrees of it. I think our last one is M62. M62 is in the same neighborhood. It's just sitting here below that. And M62, same trick. Take the middle star of the claw, go through Antares and roughly double that, and that's where you're going to pick up M62. I hope you're making notes, Samantha. This is all your tricks for finding these. Really helpful.
I can always come back to this video. So
this one's medium bright, medium sized, quite dense. So let's bring up the view. Let's see the density profile here. 22,300 light years away, and is one of the closest globular clusters physically to the center of our galaxy, the galactic core, which is in here. So that's actually, dimmed it more than it should be. You can pick with this one up in binoculars, especially when it's highest. And this is one that has a black hole, confirmed black hole inside of it. So that's neat to know. And big telescopes will show you some of its nice structure. So it's really got some structure. Stephen O'Meara has reported a blinking effect. So the idea when you look at it with direct vision versus averted vision, it seems to brighten and dim. So he's nicknamed it the flickering globular cluster. So again, this one's not perfectly round. And yeah, so look for those sorts of things when you're looking at these objects. And that's it.
So that ends our messy minutes. If anybody has any questions, I know we are right at 5 o'clock right now. Just a reminder that in the summer, we go down to 1 episode a month. So that's June, July, and August. So this has been our June episode. Our next episode will be on July 5th. And you can see our schedule on ras.ca/insiders guide that has our next topics coming up. However, we might change the next one to make it a little bit more themed. I'm excited. Chris told me about his article coming out in Sky News, and I want to hear more about it. So
yeah,
yeah.
Keep an eye on your mailbox. The July-August Sky News, I wrote about celestial objects with Canadian connections to celebrate Canada. So we might highlight some of those.
So thank you all for coming. And as I said, all these materials, I've already put it in the chat. You can find all the list of our Messier objects at ras.ca/Messier-minutes, and also a playlist of just our Messier minutes in there as well. And don't forget, the RAS General Assembly is coming up. Tickets are on sale now, and I hope to see all y'all there. And you might maybe be able to get to chat with Chris or attend one of his presentations as well. Thank you all.